Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be discussing the physics of pressure. This is an introduction to pressure. We will discuss pressure in fluids. This is a part of the series of video lectures introducing fluids or discussing fluids from an algebra-based physics perspective. Let us begin by recalling what we know so far about fluids and in general. So there's kind of two main things to recall. The first of them is the density of an object in general is defined as how much mass per unit volume the object has. The other thing to consider is forces and momentum. So forces change momentum. So this allows us to give a microscopic and then ultimately macroscopic definition for pressure. So how does the second idea tie into pressure? Well, imagine that you have a container with a fluid in it. The fluid could be really any kind of fluid. It could be a liquid, it could be a gas, it could be a plasma. I'm going to draw it as if it is a gas, but any fluid basically has some pressure. The gas consists of a bunch of little molecules that are kind of zipping around in any old direction, and these molecules are sort of contained within the walls of this container, and they really have just completely random velocity per particle, random direction, random speed that they're moving at, etc. Now, as you can imagine, if I had a collection that was behaving in the way that I've drawn this collection, the result would be that they would eventually undergo a bunch of collisions with each other and also a bunch of collisions with the walls of the container. Now, the collisions within molecule to molecule basically should conserve linear momentum within the system of two molecules or even within the system of many molecules. But each time that a molecule collides with the walls of the container, you should get a change in the momentum and therefore a change in the system's center of mass motion. In some sense, this is something that you can recall from our momentum simulation. So also recall the linear momentum simulation that I did for collisions. And for that simulation, essentially each time that a particle collides with the walls of the chamber that I put it in, you get a change in linear momentum. Well, that implies that there's some amount of force between the wall and the particle each time that a particle hits the wall. And so one thing we might ask is, well, how much force is that? And the answer is, well, these are microscopic particles, so it's a very, very small amount of force, but there's also a whole lot of them. So instead of trying to measure individual forces, maybe we try to measure an average force. So we could say something like how much force on average is applied to the walls of the container. Now, one way of figuring out an average value is to do sort of an ensemble average. In other words, we count up how many collisions there are, we add up the force from each collision, and then we divide by those number of collisions. But again, we have a whole lot of collisions and therefore a whole lot of little forces to add up in order to do this kind of average. So there's a second way of averaging. So this might also go under recall. So average doesn't always mean ensemble average like this that you learned in algebra or whatever class you learned it in. It can also mean something per something else. So for example, average speed was distance divided by time taken to do the distance. And we know that the object need not have the exact same speed at all times while moving from one point to another. We still get an average as long as we have a distance and a time. There's also such things as like population density. This is basically averaging population per unit area. And so we'd say like high population density would be like the middle of a big city, and a low population density would be out in the middle of the very rural countryside. Therefore, you have a very high population density in, say, Brooklyn or Manhattan in New York, or you have a high population density in Houston or LA, San Francisco, wherever, any of those major cities. And you have a low population density in, let's say, the western third of Kansas, or the virtually anywhere in the Dakotas or in Alaska. Okay, for most of the areas that are outside of their respective capitals and other like large towns. So in this case, we're doing the same kind of trick to get an answer to this question: how much force on average is applied to the walls? And so what we want to do is introduce another kind of average. So introducing average, and this is average force per area. That is what we mean by pressure. So pressure is how much force per area does the fluid apply. So the definition for pressure is defined as force over area. Technically, this is actually an average pressure as well, because that pressure may vary across the area of an object. And in fact, for most fluids, it would vary across the area, because as you go deeper into a fluid, you get more and more pressure. In fact, if we come here and say, how does pressure vary with depth? So how does pressure vary with depth within a fluid? And we are assuming a fluid that is basically at equilibrium. So the fluid is not really flowing about. There's no like layer here flowing down here, layer down here flowing up here. The answer then is that pressure is the density of the fluid times the free fall acceleration, or the gravity field strength, times the depth in the fluid. We could call that the D for depth, or we could call that H for height. Whoops. Let's use H for height. And this is within the fluid. You actually can add an additional P naught. So what this basically is giving you is the difference between gauge pressure. So this is gauge pressure. And then this one right here is absolute pressure. And this right here is atmospheric pressure. And so this part of the equation, this gauge pressure, is the how pressure varies with depth. We're using H to represent depth here. Okay. One more thing that we should maybe add is, what about the units? Units of pressure. There are actually quite a few units used. The sort of most important unit for our purposes is the Pascal. That's the MKS unit. So this is the MKS unit, the Pascal. 1 Pascal is equal to 1 Newton of force per meter squared of area. Now there's many other types. There are millimeters of fluid, usually of mercury, but you could use water or something else. There are torrs. There are pounds per square inch. There's atmospheres, etc. Essentially, 1 atmosphere is the pressure of our Earth's atmosphere at sea level under standard temperature conditions, not not stormy or anything like that. And this is approximately 101 kilopascals. It's also a little under 15 pounds per square inch. It's also a little over 3/4 of a meter of mercury, which is 760 millimeters of mercury, etc. So those are your units. Let's do an example to close us out. So how much force is being applied to the ground at the bottom of a lake of depth 10 meters if we have an area at that depth of 16 square meters and that it's flat? Well, our pressure should look like the density times G times H plus our atmospheric pressure. So we could call this the gauge pressure again. So P gauge is equal to rho GH is equal to 1 gram per cubic centimeter, but that is 1,000 kilograms per cubic meter. That's the density of your fresh water, times G, which is 9.8 meters per second squared, or newtons per kilogram, times H, which is the depth of 10 meters. And that means that my gauge pressure is basically 98,000 pascals. That's very close to 1 atmosphere. So quick rule of thumb with these, with fresh water, every 10 meters of depth that you add, you're adding roughly 1 more atmosphere. And actually, for salt water, it's an even better approximation for what it's worth. Like in the ocean, salt water, your density gets even closer. This means that my absolute pressure at the base is, bearing in mind that this is an atmospheric pressure, means it's about 101,000 pascals. That means my absolute pressure is 199,000 pascals. And so now we ask, how much force is it? Well, pressure is defined as force per area, and that means that force is pressure times area. That means that my pressure, force, at the bottom of this lake should end up being, for total, about 3,184,000 newtons. And so if we round this off to 2 significant figures as warranted by all the numbers we're given up here, this is about 3.2 meganewtons of pressure, or 3.2 million newtons. All right, well, that's all for today's video. Hope that you learned something in it, and as always, thanks for watching.